Now I have a definition here at the top of the page. It says a series that is convergent but is not absolutely convergent is called conditionally convergent. And the note says the alternating harmonic series converges conditionally. So the harmonic series is this, okay? The alternating harmonic series looks like this. By the alternating series test, we can show that the alternating harmonic series converges, but it's not absolutely convergent, because if you take the absolute value of this, you're back to the harmonic series, which we've shown before diverges. So we sometimes have a series, an alternating series that is conditionally convergent. It converges because some of its terms are positive and some of its terms are negative. If all of the terms were positive, the series would not converge. So it's not absolutely convergent. And I'm going to show you an example of it here with this first one. This first one is the series from n equals 1 to infinity, and we have -1 to the n over 1 over n plus 3. This is not an absolutely convergent series, because if we were to look at the absolute value of these terms, it would eliminate the -1 to the n. If we were looking at the absolute value here, we just have 1 over n plus 3. Now, if our series was just 1 over n plus 3, then if we were to use the limit comparison test with the harmonic series, we would have this. So we'd have 1 over n plus 3 over 1 plus n, and that is the same thing as saying n over n plus 3. You divide everything by n, and there's a limit in front of this, I'm just running out of space. Divide through by n, and you'd have 1 over 1 plus 3 to the n, or sorry, 1 plus 3 over n, not 3 to the n. Again, you're taking the limit of this, which is going to be a limit of 1. So by the limit comparison test, 1 over n plus 3 would diverge. So what does that tell us? It tells us the series does not, it is not absolutely convergent. However, let me make a note here. It's not absolutely convergent. That's supposed to be an O. However, it might be conditionally convergent, and it is. We can go back to the alternating series test to show that this is conditionally convergent. So remember, there's 3 criteria we're looking at for the alternating series test. 1, are the u sub n values all positive? So u sub n here is going to be 1 over n plus 3. Since n starts at 1 and gets bigger, yes, those are all positive. Second criteria is u sub n greater than or equal to u sub n plus 1. And in this case, you'd have 1 over n plus 3 greater than or equal to 1 over n plus 1 plus 3. Cross multiply, n plus 4 greater than or equal to n plus 3. Yes, this holds true. So that's the second criteria. Third criteria says as n goes to infinity, the limit of u sub n is 0. And again, that is going to be true. So it is conditionally convergent by the alternating series test. So when you have an alternating series, it may not be absolutely convergent, but it might be conditionally convergent. And this is something that'll happen only with the alternating series. The second one here, we have the series from n equals 1 to infinity, -1 to the n times n plus 1 to the nth power all over 2n to the nth power. This one I'm going to go ahead and test for absolute convergence right off the bat, and I'm going to use the root test for this one. So I'm going to look at the limit as n goes to infinity of the nth root of the absolute value of -1 to the n times n plus 1 to the n over 2n to the n. Now the absolute value bars is really just going to eliminate this -1 to the n. It's going to make everything positive. N plus 1 to the n and 2n to the n, they're already going to be positive because our n values are positive. So I don't need the absolute value bars anymore. When I take the nth root of n plus 1 to the n, I just get n plus 1. The nth root of 2n to the n is just going to be 2n. So what I have now is the limit as n approaches infinity of n plus 1 over 2n. And if I divide through by n, the limit as n approaches infinity of 1 plus 1 over n over 2. As n goes to infinity, 1 over n goes to 0, so our limit here is just 1/2. And with the root test, as long as this value, which we call rho, as long as this value is less than 1, which it is, we say the series converges absolutely. And since it converging absolutely is a more stricter set of circumstances, it would also converge conditionally, but in this case, it converges absolutely. It holds that higher standard.